All right, so the take-home message is this. If you look at the graph in the top left-hand corner, it's titled Renal Autoregulation. You can actually see in the face of varying mean arterial pressure, you can go from 80 millimeters of mercury to 180 millimeters of mercury. That's very high blood pressure. You can see that the flow rate, GFR, and renal blood flow stay the same. That's actually really incredible, that GFR and renal blood flow can stay the same, stay constant in the face of varying mean arterial pressure. And that's all due to those autoregulatory mechanisms: myogenic regulation, tubuloglomerular feedback, and mesangial control. So that's pretty amazing. And again, it's why those intrinsic mechanisms are so important. All right, so let's go to the top right-hand graph. And I want you to remember those graphs, those diagrams where we actually constrict or dilate the afferent or efferent arterioles and what happens to GFR. This is just a graph showing you what happens as you increase afferent arteriolar resistance. You can see GFR actually plummets as you do that, as well as renal plasma flow. Now, in the bottom left-hand graph, you can actually see as you increase efferent arteriolar resistance, GFR increases slightly, but then because of these autoregulatory mechanisms, it will also start to fall as you increase efferent arteriolar resistance. Renal plasma flow, as you would expect, will fall again as you increase efferent arteriolar resistance. And then the bottom right-hand graph is showing you the relationship between GFR and plasma creatinine levels. Again, plasma creatinine is a breakdown product, a metabolite of creatine, and it's produced by the body, and it's usually eliminated from the body through excretion, urination. So you can see as GFR falls, and this would be indicative of kidney failure, if the GFR actually fell to about 15 liters per day, you can see plasma creatinine levels skyrocket because you're not able to filter and get rid of this metabolite. So again, creatinine levels, if GFR is very low, 15 liters per day, you can see that plasma creatinine levels will skyrocket to about 16 milligrams per deciliter. So not a good thing, but as GFR increases up to 90 liters per day, you're actually really filtering out and getting rid of those creatinine levels from the body. All right, so the last question I'm going to pose in this lecture is, why is it important to measure GFR? It's important to measure GFR because it tells clinicians about an individual's kidney function. So normally an individual has a GFR of around 100 mils per minute. It's adjusted by body surface area of about 1.73 meters squared, but 100 mils per minute is basically a normal GFR. If a patient actually has a GFR of around 15 or less, that's technically stage 4 kidney failure. So knowing something about GFR tells you something about kidney function, and so it's really important to know that parameter. We're going to learn how to calculate GFR using something called a clearance equation, and we're going to use creatinine, which is a great marker for GFR. We're going to plug all the parameters for creatinine in the clearance equation, and technically when we do that and we calculate creatinine clearance, we're technically calculating GFR, and we're going to learn about that in the next couple lectures. So again, why is it important to measure GFR? GFR is telling you something about a patient's kidney function.